Ever wonder why a rubber band stretches but a twig snaps? Or how bridges hold up thousands of cars? It's all about the science of materials. Everything around us deals with forces, pushes and pulls that can bend, stretch, or break things. Engineers must predict how much a material can handle before it changes shape or breaks. The key concepts: stress and strain. Stress is the internal resistance when you apply a force. Strain is how much the material deforms. Understanding these helps us design everything from trampolines to skyscrapers. Let's dive into the world of stress and strain. Mechanical stress is the internal force per unit area within a material when an external force is applied. The formula is simple: stress equals force divided by area. Imagine pushing a thumbtack into a corkboard. The tiny point means high stress, making it easy to push in. Try the same force with a coin and nothing happens. The area is too large, so the stress is low. For example, if a 100 Newton force acts on a rod with a 0.01 square meter area, the stress is 10,000 pascals. Stress tells engineers exactly how much internal force a material is experiencing. High stress can cause failure, so engineers design parts to spread out forces and keep stress low. It's all about distributing the load to keep things safe. Stress isn't just a concept, it's a measurable value that guides real-world design. That's why understanding stress is crucial in engineering. Now let's talk about strain, the result of stress. Strain measures how much a material changes shape under force. The formula: strain equals change in length divided by original length. Pull a 10 centimeter rubber band to 12 centimeters. The strain is 2 divided by 10, or 0.2. Strain has no units. It's a ratio or percentage of deformation. This lets engineers compare how different materials deform no matter their size. Stress is about internal force. Strain is about how much something stretches or compresses. A small stretch is huge for a paperclip, but minor for a bridge cable. Strain standardizes deformation, helping engineers predict real-world behavior. That's why strain matters in every design. Stress and strain are two sides of the same coin, especially for materials like steel and aluminum. When you increase stress, strain increases proportionally. This is Hooke's law. The formula: stress equals Young's modulus times strain. Young's modulus measures stiffness. A high value means the material is hard to stretch, like steel. A low value means it's flexible, like rubber. Engineers use Young's modulus to predict exactly how much a material will stretch or compress under a given force. This lets them design bridges, wings, and buildings that flex just the right amount, never too much. Tables of Young's modulus values help engineers pick the right material for every job. This predictable relationship is the foundation of safe, reliable engineering. Stress and strain together make modern design possible. Let's see stress and strain in action. Think of a suspension bridge. Steel cables hold up the roadway. When cars drive on, their weight creates stress in the cables. The cables stretch slightly. This is strain. Engineers calculate the maximum stress and use Young's modulus to ensure the cables only stretch within safe limits. Stress is internal force per area. Strain is the proportional deformation. Stress is measured in pascals. Strain is a ratio. Understanding this relationship is essential for safe bridges, buildings, and everything in between. That's the science behind the structures that shape our world.